going to start by telling you something that you already know, but you might not have really thought about too much, which is that networking is important. It used to be that networking was just the way we reached our users. So they're out there on the internet somewhere, and they connect into our single server somewhere in a data center, and we didn't need to think about it too much. But over time, like our ambitions for applications have like outstripped even Moore's law. They've gone through the roof. We're now building applications using microservices, VMs. We're using like all these technologies that we know and love, and it's starting to look a lot more like this. So the network is becoming a key part of the application that runs right the way through it. So when you're hitting a REST API, you're making a network call. It might go local to your machine. It might go across the internet. It might go to another machine in the same data center. But the network has become integral to our apps. And not only that, but the network is getting bigger and bigger. Like the number of things we're putting on there is going up. So I'm going to talk about that. But the point of this talk is really to tell you some of the things that come up time and time again that we think are really important about networks and what you should be thinking about when you're choosing a network provider, choosing a network fabric for your Kubernetes cluster or your Mesos cluster or whatever. And the first thing is kind of echoing the talk this morning by Ramana. They think the same thing as us. Like IP is really important. IP is where it is. Like the we think we should put IP right at the center of networks. Your applications these days don't talk, NetBIOS or Apple talk. They don't even need kind of Ethernet broadcast most of the time. And things get a lot simpler if we start with IP being the focus. So that's going to kind of run through the talk. And the first thing that I think is really important about networking is operational simplicity, and hopefully I'll be able to convince you with a counterexample. Okay, so what's the counterexample? Counterexample is overcomplexity. So my colleague Christopher, a few years ago, he was working at a bioinformatics company. He was managing that OpenStack cluster. Mistake number one, I know, but it came time to upgrade the cluster, going Essex to Folsom if there are any OpenStack nerds in the room, and the networking broke. So he goes to diagnose it. He starts digging through log files. He starts snooping traffic. And after an hour, like he found some kind of clue about what was going on, but 36 hours later, he still couldn't fix it, and he had to roll back the upgrade. So why is that? Like what was really going wrong here? And the problem is that for reasons that apply mostly to kind of legacy workloads, like VMs and people migrating to the cloud, we built this very complicated network in OpenStack, and diagnosing that is really, really hard. So Christopher's a network guy. He's been in the networking industry for a very long time. He's built intercontinental IP networks, like backbone networks for major providers like Telstra, and he got to thinking, well, Can we do something better? Can we do something more like the internet? And this is kind of where like Kubernetes networking is kind of going already. Like this is a lot of the ideas in Kubernetes kind of follow the same path and for the same reasons. But I just wanted to give you a feel for it. So this is like a diagram of a kind of corner of the internet somewhere, and it's quite a simple data path when you really boil it down. So you have a bunch of hosts. Each of your hosts is running services. Each of them has an IP address. The IP address is known about by the router that's nearest to the host. The routers communicate to distribute the IP addresses that they know about, and packets get routed, which means you have an IP packet coming out of there. It hits the router. The router consults its routing table. Sorry, I lived in America for a while, so I kind of flip between routing and routing in the same sentence. So it hits the routing table, and that router knows where to send it because the routing table covers the whole internet. So can we build something that looks more like this for container networks and VM networks and that sort of thing? Well, this is what Calico does. So we put a router on each of the hosts, and we connect your pods or your containers or your virtual machines into the router, and then we route packets, and we do basically the same thing that the internet does. So this is a kind of quite a simple network design. So comparing it with the previous one, Christopher can diagnose one of these that spans continents in about 15 minutes and have it back online. So that was where he was coming from, and he's the architect for Calico. Just in a little bit more detail. So this is zooming in on one of those hosts. You've got your container namespaces, so pods run in a container namespace, like they have their own kind of network stack. They see their own network devices. Then poking out at each one of those is a VETH device, so a virtual Ethernet device, I think that stands for, and we connect it into a router. But is that something else that we have to drop onto your host? Well, no, it's not. It's not another application that we're dropping on there. It's not another program that has to deal with the packets. It turns out that the Linux kernel already has one of these. It already has a router built in, and it's stable, and it's been in the kernel for years. Like it's a hardened, production-ready routing table implementation. So we use that, and that's another thing to look for in anything you buy. Is it using kind of proven technologies? And then for local containers, we program a route for each of those containers. So we do have an agent that runs on each of the hosts. It's called Felix, and that programs a route into the routing table for each of the local containers. And then we learn the routes for all the other workloads on the network by talking to the other routers in the network or pairing with the other Calico hosts. One thing to notice here is we've programmed a full /32 route on the local host, but for workloads on other hosts, we're able to aggregate, which is how the internet manages to scale. So we're able to program in this case /26 routes that cover a whole range of IP addresses. That keeps the number of routes that we have to program into the kernel nice and low. So the kernel can handle 1 million routes if you want to throw them in, but we don't need to do that. We can take advantage of the natural kind of grouping of IP addresses, and then if you allow us to take control of IP address management, we also deliberately allocate IP addresses that are easy to aggregate in this fashion. Cool. So operational simplicity, that's kind of number one. And something I want to emphasize here is if you want to diagnose this network, you can use ping and traceroute and things like that. So you can ping something and see where the packet goes. You don't need to worry about layers of overlay, complexity getting in the way, like we had in the OpenStack example that was kind of making it impossible for even a networking guru like Christopher to figure it out. Cool. So that's operational simplicity. Scalability, that's the second thing I think you should be thinking about. So who can tell me what this graph represents? Or who's seen this one before? Shout it out. Yeah, that's right, Moore's law. So this graph comes from Gordon Moore's paper where the phrase Moore's law comes from. And what it shows is, he'd observed this trend in the industry where as the number of components you put on an integrated circuit goes up, the price varies per component. And then if you plot that year on year, so each graph is a different year, then the price per component at the sweet spot at the bottom of each of those curves was going exponentially over to the right, which means it's better to you get cheaper components if you make them more dense, and it was going exponentially down, which is something that we don't always think about, which means everything's getting cheaper. So you should be saving money exponentially with these trends. So what does it look like today? Well, here's Amazon's EC2 pricing. Like, the trend continues. Like, the pricing's fallen through the floor in, you know, kind of just a few years, so just kind of 4 years, and it's gone down by 60%. And what's driving that sort of thing? Well, each individual host is getting bigger and cheaper, and at the same time we're virtualizing, we're carving it up into VMs, we're carving it up now into containers, and we're getting back to this, where if you're building applications in this environment, we're dividing them up into smaller and smaller pieces so they can be more fluid, and we can move them around the network and scale them out and scale them back, and the scale of like the number of components in our applications going up. The number of endpoints on any particular host has gone from 1, where you have just an IP address per host, to 10 when you've got VMs, and now like maybe 100 when you have containers, maybe 1,000 next year. So the scale of your network, even though we're just kind of taking advantage of these cost savings, is going through the roof. Combine that with the fact that we're also talking about really short lifetimes for containers versus even VMs, and the rate of churn in your network is going up and up and up as well. So, you know, maybe a VM lasts for a week or a day, but a container is, you know, is cattle, not pets. You spin one up for 5 minutes, knock it down, spin the next version up, knock it down, deploy 16 times a day, all these kind of things. So the rate of churn in the network's going up, so you need to care about the scale of your network. So got a video. This is one of our routine scale tests for Calico. And here we're starting 50,000 containers. We spun up 500 hosts in GCE. This isn't running Kubernetes. It's just kind of starting as many containers on each host as we can. And we can start about 50,000 containers in 5 minutes. And if you see at the bottom of the screen, not sure if you can all see it, but we're measuring the time to first ping. So that's when does the network come up. So when is the container booted, and then like how long does it take from the container being booted to when it can contact some other container and get a response back. And so that's kind of holding steady at about 8 milliseconds as we're starting 150 containers per second. And jumping ahead a little bit, towards the sort of next section of my talk, which is about security, we're also imposing security rules in this test. So each of these containers that's coming up, we have to impose security rules at the container itself and at the destination that it's trying to ping in order to whitelist the traffic between them. So scalability is something you should look for, and if you think that sort of scale is good, then look at Calico. So those are the first two things. As I kind of alluded to, the other thing I think you should look for is security. So why do I think that? Okay, so this back in November 2014, Sony employees came in to find this on their desktop. And it wasn't a new corporate rebranding exercise. It was, we now think, an attack by North Korea in revenge for making a film that they didn't like. But by the time they managed to shut this attack down, about 800 of their 1,500 servers had been knocked offline, and half of their desktop machines, of which they had 10,000 or something, had been obliterated, and they lost all the files and had to rebuild them from scratch. So that's not good. What had they done wrong? How were the hackers able to make it into their network and then destroy it? So the FBI did an investigation. So James Comey, I'm not sure if I said his name right, wrote a book about the hacking. And just to pull a quote out of there, once the invaders made it past the network gates, they could go anywhere they wanted because Sony hadn't locked any doors. So once they got through the outside of Sony's network, then like there was nothing stopping them inside. They could get from one machine to the next. And we like to call that the Armadillo model. So it's really hard on the outside, like they've got firewalls in place, they harden their network, but once you're in, it's soft and gooey on the inside. So yeah, once the attackers had a beachhead inside Sony's network, they used that to launch other attacks. And the thing to look out for here is, like, why did this host over here have access to all these other things? Like, you've got this complete cross product. You can talk to anything. You've got a huge attack surface. So once you've compromised one node, you can go on to attack each node in sequence and see if you can figure something out. Now, how can we do better? Like, what did we used to do? Like, well, we used to divide our applications up into 3 tiers, and then we'd put a firewall between the 3 tiers. And then we had a firewall admin, and we'd pay him, and we'd say, okay, now I need to open up a new port. Please can you open that port up for me? And that worked great when you had 3 tiers, and they were all very homogeneous. But like, this is the world we live in now. Like, we're starting, hundreds of microservices to deliver like the overall application. It doesn't fit this model. And then if you try to apply it to, a container orchestrator like Kubernetes, the only place you can put a firewall is around the outside of the Kubernetes cluster. And then that gets you back here, where all of the pods can talk to all of the pods. That's not great. So what do we do? Well, this is what we'd really like to be able to do, right? So what we want to do is capture the developer's intent. So we want to open up just the connections that we want to open up, that we need for our application. So Cassandra listens on port 1234. We want to enable the specific applications that need to talk to Cassandra to be able to talk to it on port 1234. And we got this great opportunity now with like containers and like the way we're specifying applications. So like when you write a YAML file that specifies your pods, we've got a great opportunity to be able to add this security information right in there. So you can't start a Cassandra node without telling it without telling it the right ports to open up, and you can't connect to it without like annotating your client to at the sort of admin level to say, right, this is an allowed client to talk to Cassandra. So that's what we'd really like to be able to do. Like, just get to something like this, where if one pod gets compromised, well, you can only go along the lines that are really, really needed for the application. So your load balancer can only talk to your front ends. Your front ends can only talk to your like mid-tier. Your mid-tier is the only thing allowed to talk to your database. Your management API is allowed to talk to anything, but nothing can talk to your management API unless it gets connected to first. These kind of things. So that's where we'd like to get to. And with Calico, that's what we're working on. So how can we kind of bring this into the Kubernetes cluster? Well, the only place we can put a firewall is right at the edge. So we put it right in front of each of the veths coming out of the namespaces, and we calculate the firewall rules just for that particular container and insert it into the Linux kernel using its IP tables firewall that's baked in. So that's another kind of production-ready, like hardened networking piece that you already have because it's baked into the Linux kernel. And by using by putting a router in that place instead of a bridge, which some of the other networking technologies do, it's a little bit easier to get this all to hang together and make sure that nothing gets bridged when you're on the same node. Not impossible, but that's a slight advantage of having a router there. And as it happens, I have a demo of exactly this. So I just want to say the networking special interest group in Kubernetes is working on a policy specification for defining all these rules, and we've been part of that process. So I'm going to demo the V1 Alpha 1 version of that API, and that's something that you can download and try today. And if you have any comments or feedback about it, then let us know. But yeah, so how does that look? So I'm just going to alternate between slides that explain what I'm going to show. So I'm going to start up default namespace, which we have by default in Kubernetes. And then I'm going to start up some front-end pods. And these are just running a kind of test app that's going to try and connect to everything. And some back-end pods. And then I'm going to impose policy that allows just them to talk to them. I'm going to start up a separate management pod. The management pod is going to display a GUI for us so we can see what's going on and see who can actually talk to who. And I'm going to start up a client pod in a client namespace. So that's kind of simulating the outside world. And then these are the connections that are actually required by the app. But these are the connections that you'd get, or the kind of places where you could make connections by default, and I'm gonna block those. So let's start up the demo. So we call this the stars demo. So just kicked off all those different services. So if I look in that folder, I've got a backend YAML, a client YAML, a frontend YAML, and a management UI.yaml. So just to show you one of those. So there's nothing too exciting. This is all kind of standard vanilla sort of 1.1 Kubernetes, like nothing exciting yet. So we're starting a backend. We tell it what ports and so on to listen on. We're labeling it with tier backend. So we're going to use that in the policy later. So that's this bit here. Oh, sorry, that's the replication controller to make sure we have multiple of them. But we're going to label with tier backend, and then that's it. So we're just starting up that particular container. Front end similar. Management UI I'm going to connect to in a minute, and then let's just check everything's running. So everything's running. So with a bit of luck, if I refresh the demo. So this is the management UI showing that everything can connect to everything at the moment. So we've got this full connectivity. But what we really want is for the client to be able to talk to the front end and the front end to be able to talk to the back end, but everything else to be blocked. I should say there's actually multiple pods running behind each of these services. So it works with services too, but the UI isn't capable of showing that. So next step is to turn on isolation. So this is new in Kubernetes. I think it's experimental in 1.1, I think. So this is a flag you can set on each namespace to turn on or turn off isolation. So that tells Kubernetes whether you want any policy at all. And once you turn it on, we should lose all connectivity. So it'll look like this once I turn it on. In fact, we'll lose the UI because the UI can't connect to anything. So with a bit of luck, I can pull this out of my oh, what have I done? I think that should be default. There we go. So I've annotated those two things, and what should happen is if I refresh this, then after a little while, we'll get no connectivity at all. So it takes a few seconds for the UI to update. It has this comedy state in the middle where it can connect to one thing and the GUI all breaks down. But there we go. So after a few seconds, the UI is caught up, and like we've got no connectivity. So the management UI can't even detect the pods anymore. It can't connect to them. So that's not very useful. But let's start adding back in some policy. So let's let the admin UI connect to everything. So this is an example of policy using the new Kubernetes API, and starts with a bit of metadata. So you define what type of object you want to put in Kubernetes, and right now this is kind of done as one of these third-party objects. So although the spec is defined by the Kubernetes SIG, we're putting it in as a third-party object. Then you have a specifier that tells it what pods should this policy apply to. So in this case, it's empty. So that means this applies to all of the different pods in a namespace. And then you have a set of rules. So here I've only got one rule, and that rule says allow packets to come in from the namespace management UI and anything within that. So this is going to allow the management UI to connect to everything. So that's what I want. So if I do pull it out of my, there we go. Obviously drop that in a different place this time. Okay, so I've added that policy, and I've got two namespaces, so I had to do it twice. And then if I refresh this, then we see all of the pods again because the management UI can connect in. And then I've got some policy for the backends, and this time I'm selecting the backends and saying I want to only allow. So I'm selecting the backends. They're the ones that I'm policing the traffic for, and I'm saying allow protocol TCP port 637, but only allow it from pods that match this other selector tier frontend. So you could get a lot more complicated with this, but in this simple case, like we just want to say if it's a frontend, it's allowed to talk to us. So this is what we're aiming for. So I'll throw in the backend policy. Again, it might take a few seconds for this to wake up. There we go. So the front end can now talk to the back end, and it's a one-way connection. So we do stateful packet filtering, so the packets can come, like response packets can go back from the back end, but the back end can't just talk to the front end. And then for the front end, similarly, going to pick out the front ends as the things that I want to apply policy for, and then I'm going to say allow from anything in the client namespace, and allow TCP port 80 because it's the front end with a web server. Aiming for this. So should just have front end policy, and then after a few seconds, the UI will pick it up, hopefully. There we go. There we go. So that's the end of the demo. Cool. So what I've shown there is we've blocked all of these different connections, and all of those could be attack vectors in your network if someone compromised a pod. We call this the principle of least privilege, where you only open up the things that are absolutely needed, and everything else is blocked by default. And I had a video back up which I don't want. So let's get into the end of the talk. These are the 3 things that I think you should be thinking about when you're choosing a network technology. These are the things that we design Calico around. So operational simplicity. Can you debug it with ping and traceroute when you have to? Because you will have to at some point. Does it scale? Because the way we're building applications now and the challenges of the marketplace and the fact our competitors are coming in and pushing us to scale and build more features means that your network needs to scale. And is it secure? Because if it's not secure, then it's a house of cards and it's all going to fall down. Cool. So you can find more about Project Calico at projectcalico.org. We have a production CNI plugin for Kubernetes, so that's the kind of best way to try out Calico and try it out with Kubernetes. We've got documentation that tells you how to set it up with CoreOS and Ubuntu, and we've got vagrant quick starts and that sort of stuff. This demo that I did today is something that you can try out. It's for yourself, so that's that other link. And then our friends at KubeSray have made some Ansible playbooks for deploying Kubernetes, and they support Calico, so that's another way to try it out. If you want to ask questions about Project Calico, we all hang out on the Calico users Slack, so you get pretty quick turnarounds, and if you have any bugs or anything, we're on GitHub, and you can file an issue there. So if you want to follow me, I'm FazXC on Twitter. You follow us at Project Calico. Cool. Thanks, Brian. Question is, are we going to help with kind of when you go to kind of Kubernetes and you have multiple clusters and you want to manage the security between the clusters? Can we help there? So those sorts of features are on our roadmap for sure, and we plan to kind of federate and allow policy to refer to other things in other clusters and that sort of stuff, but we don't have that today. You can, apart from referencing kind of front-end workloads and that sort of thing, you can drop in rules that say allow from this CIDR block, or you can do that kind of coarse-grained stuff to deal with things in the outside world. And because we're an IP-based fabric and it's rooted, we work with standard kind of VPN type technologies, and we should work just fine over things like IPsec. Some of our customers are experimenting with that. Do we have a plan for how to go multi-tenant? So our policy is kind of agnostic to whether you're using it for defining tenants or whether you're using it to isolate different workloads. So something that maybe doesn't come out there is like our policy is kind of ordered, and we have the ability to do things like tiers in our policy. So you could have something like a tier that's owned by your NetSec team, and the NetSec team can enforce various kind of global rules like completely isolate this namespace from this namespace because they belong to different people, and then nobody can override that because it's at a higher tier and it's owned by the NetSec team. But then when you come in to have your developers define the precise kind of port level policy, they're not allowed to open up into the other tier. So we don't kind of explicitly have anything that supports tenants, but if your orchestrator supports tenants, then the plugin into the orchestrator can map those concepts onto Calico concepts very easily. Does that answer the question? So the question is, do we have any plans to automatically figure out the security graph and do the securing? So we don't have any plans to do that, but it's one of those little ideas that keeps coming up of like, could we have a sandbox mode or something along those lines where we just monitor? We do have some things on the horizon to do kind of monitoring and kind of analytics and stuff on like what's being dropped, but that's kind of slightly different. Question was, does it work with OpenShift? We've never tried it. I've been trying to grab someone from the OpenShift team. I saw a few milling around to ask and try and figure that out. If OpenShift just kind of deploys Kubernetes with a bunch of other stuff, then it should plug right in, because we're just a straightforward Kubernetes CNI plugin. But I don't know the answer. One way at the back there. So the container benchmark that I showed earlier. So the policy there, we divided up the containers into like, I think 100 different groups, and we imposed policy that said each container can only talk to the other containers within its group. And then when each of those containers started up, it picked a kind of distinguished member of the group that we called a ping target, and it started pinging that and then measured the time. So that's why we have to put policy in place at the ping target and at the actual container that's being started up. But one of the things that we do is we only apply the policy that's actually relevant to the particular host. So we filter out all of the IP tables rules that wouldn't be needed on that particular host, because there's no workloads that match that particular policy on that host, and apply it that way. Cool. Yeah, at the front.
Do you also filter outbound traffic? Can I use
Filter outbound traffic? Calico absolutely does. I'm not sure if the Kubernetes policy spec allows you to filter outbound traffic yet.
Yeah, there's no limitation. I mean, you're free to do what you want.
Yep. Cool. Are we at time?
If people still have questions, feel free.
All right. I think we're running dry. Cool. Thanks, guys.